In the last lecture, we mentioned about the shielding constant. We said that the actual magnetic field experienced by the nucleus will not be equal to the applied magnetic field, because the surrounding electrons produce a magnetic field and oppose the applied magnetic field. So Hn equal to H0 into 1 minus sigma, where sigma is called the shielding constant and sigma is dimensionless. And this Hn will depend upon what are the atoms attached to the particular nucleus. Suppose an electronegative atom is attached, it will attract all the electrons. So the electron cloud around the nucleus will decrease. Therefore, the field that produces will also decrease. So the nucleus may experience the field that is applied as it is. So number of parameters are there which contribute to the sigma value. Now, this Hn and H0 are very difficult to measure accurately. Therefore, we add a reference material whenever you record an NMR spectrum. What are the reference materials which we use? If it is a proton NMR or C13 NMR, we use tetramethylsilane. This is the structure for that. So this is the reference material. So whenever you record a spectrum, you will add a drop of TMS into the sample. It is an internal standard. This material is an internal standard. We can add to the sample and record. This will absorb at the highest field. So with respect to that, other protons are absorbing at different fields. We measure that. So this is the internal reference for proton NMR as well as C13 NMR. Similarly, if it is F19 NMR, we use CFCl3 as the reference material. For F19 NMR, the reference material is CFCl3. This is the reference material. This is also used as the internal standard. That is, you can add this to the sample and record NMR. P31 has also a spin of half, so you can record phosphorus NMR. And for phosphorus NMR, H3PO4, phosphoric acid, is the reference material. But the problem is you cannot add this to the sample, it is acid. So some reaction may set in. So we use it as an external standard. Say you use say your sample tube should be a double-walled vessel. In the outer wall you add phosphoric acid, and inside you add your reference material sample and record the spectrum. Okay, these are the standards, reference material. So with respect to the reference material, where does your proton or C13 etc. absorb is the question. Now, it is very difficult to measure H0 and Hn accurately. Therefore, we are adding a reference material, I said. The difference in shielding constants, let us say the shielding constant for the sample is sigma s, and the shielding constant for the reference is sigma r. This difference is known as the chemical shift. Some people use the term isomer shift also. Chemical shift is the correct definition, which is equal to sigma s minus sigma r, or I can even write it as it is hs minus hr, field at which the sample absorbs minus field at which the reference material absorbs by hs. This is the definition for delta, the chemical shift. Or I can write is equal to the frequency at which your sample absorbs minus the frequency at which your reference material absorbs over us. This is the definition for the chemical shift. So different protons, depending upon the electronic environment, depending upon to which atom it is attached, absorb at different delta value. So delta value is a very, very important parameter, and that is defined by the radio frequency at which your sample absorbs minus radio frequency at which your reference material absorbs over s, the frequency at which the sample absorbs. Now, the quantities s, nu r, etc. are large quantities. Therefore, only a very slight difference will be there between the fixed frequency and s. By fixed frequency, what I mean is, say 60 megahertz when we record a proton NMR, low resolution. So instead of s, I can even write as nu naught. So this is the frequency at which the sample absorbs, this is the frequency at which the reference material absorbs, and this is the frequency of the probe. Okay, and this quantity which calculate will be very small. Therefore, to make it measurable, and what I mean, we multiply this by 10 power 6 and make it a big number. So it will be convenient to refer to that values. So therefore, the unit for chemical shift is ppm. Parts per million is the unit for the chemical shift. Now I will talk about what is meant by spin-spin splitting, or I can call it spin-spin coupling. Can use any term. What I mean by this is, say I have an atom H on one carbon atom and an atom HB at another carbon atom. Provided these two have different chemical shift values, I have not indicated what are the other groups. If they have different chemical shift values, this will interact. HA will take two different orientations with respect to HB, and HB will take two different orientations with respect to HA. So we say that they will couple with each other, and because of this, the signal will be split. Let us say this is the signal for HA and this is the signal for HB. They absorb at different chemical shift values. Now we said when they couple with each other, this signal will be split into two and this will be split into two. So the actual spectrum will look like this. So this is the signal of HA and this is the signal of HB. This is what is called the spin-spin coupling or spin-spin splitting. On the adjacent carbon atom, how many protons are there? Plus 1 will be the splitting pattern. For HA, there is only one proton adjacent on the adjacent carbon atom. So it is N plus 1 is the splitting I said. This formula is applicable only for the proton. So this will become 2 and this will also become 2. The general formula can be mentioned as it is 2Ni plus 1, where N refers to the number of nuclei on the adjacent atom, I is the spin of that nucleus plus 1. In this case, on the adjacent carbon atom, as I mentioned earlier, only one hydrogen is there. So N is equal to 1 here. And the spin of the proton is half plus 1. So it will be equal to 1 plus 1, 2. That's why you get a doublet. Suppose I have an atom whose spin is 1, not hydrogen, an atom whose spin is 1. Then it will be 2 into 1 into 1 plus 1, it will be split into 3. And let me give an example. Say I have a compound CH3, CH2, Br. This carbon is attached to an electronegative atom. So electrons will be attracted by this atom. It will not be shielded because the electrons have shifted. So this will absorb at a low field, and this will absorb at a high field. So the spectrum will look like this. CH2 will absorb at a low field, and CH3 will absorb at a high field. Of course, you have TMS here, the reference material. Right. As I mentioned earlier, if you measure this area, this will correspond to 2 protons and this will correspond to 3 protons. If I talk about the splitting pattern now, adjacent to this, there are 3 protons. If you use the N plus 1 formula, so this line will be split into a quartet, 4. Or as I told you, if you use this formula, 2N, 2Ni plus 1. Two into N is equal to 3 here. I of proton is half plus 1. So it will be 4. So this signal will be split into a quartet. And this signal will be split into a triplet. So I can depict it as CH2 signal will be a quartet and this will be a triplet. This will be the type of spectrum which you will get for CH3, CH2, Br. TMS, the reference material, absorbs at the highest field, and this CH2, which is attached to a bromine, absorbs at a low field, and CH3, which absorbs at a relatively higher field. This signal, due to the 3 protons on the adjacent carbon, split into a quartet. And this signal, adjacent to methyl isolate quartet, and the signal of the methyl adjacent to this will be a triplet. Okay. One more thing is, what will be the intensity of these signals? In which ratio? We talk about splitting pattern. In which ratio will be this signal? I mentioned that these protons, the carbon containing these protons, is attached to a electronegative atom. So electron density will be attracted by this bromine. Electron density will be less here. So that will cause a less shielding effect. So these protons are not shielded. So they will absorb at a lower field itself. And this will absorb at a higher field. TMS at the highest. So this will be the type of spectrum. This is for the CH2 and this is for the CH3. Intensity ratio is 2:3 and the TMS here for the 12 protons. As far as the splitting is concerned, adjacent to methylene there are 3 protons here. So this will be split into a quartet. So this will be a quartet. Adjacent to methyl there are only 2 protons. So this will be split into a triplet. This will be the type of curve which you get. Then, what will be the intensity of the split peaks? They may not be equal, it is like this only. To mention about this, you must be familiar with what is called the Pascal's triangle. Namely, 1, if it splits into a doublet, the intensity will be 1, 1. What I have done is, I have added a 0 here and a 0 here, and I am adding 0 plus 1, 1, 1 plus 0, 1. Then this will be same thing, 0 plus 1, 1, 1 plus 1, 2, 1 plus 0, 1. Hope you follow. So if it is a triplet, the intensity ratio will be 1:2:1. I am writing for a quartet now. 1, 2 plus 1, 3, 2 plus 1, 3, 1 plus 0, 1. 1, 3, 3, 1 will be the intensity ratio. So, keeping that in mind, I have drawn like this. A quartet will be 1, 3, 3, 1. A triplet will be 1, 2, 1. So, this is how you get the spectrum. So, that's about the splitting pattern, or what you call as spin coupling is the name given to that. Now, let me draw the spectrum of proton NMR spectrum of ethanol. This hydrogen is attached to an electronegative atom, so it is de-shielded. That means it will absorb at a low field. Then it is methylene. Then it is CH3. What will be the type of the spectrum which you get? The spectrum will be like this. This is the TMS peak. It will be always there. And the OHP will be at a low field, I said. So this will be the OH peak. Then it is CH2. Then it is CH3. Now adjacent to this proton, you have 2 protons. Therefore, this will be split into a triplet. Adjacent to this methyl, there are 2 protons. So this will also be split into a triplet. As far as these protons are concerned, on either side you have protons. So it will be split by this methyl group as well as this OH group. So by methyl, it will be split into a quartet, and by this OH, each line will be split into a doublet. So it will be an octet here. It will be an octet. To simplify this, what we do is you slightly acidify this ethanol. Put an acid, H plus. The functional group proton will undergo exchange with this. This H will go there, that H will come here. So exchange will take place. Whenever exchange takes place, the splitting cannot be seen. Therefore, if I slightly acidify this ethanol and then record a spectrum, I get a signal for OH like this. I get a signal for CH2 and I get a signal for CH3. I said that whenever fast exchange takes place, it will not undergo splitting, it will not split the other protons also. So the OH proton will be only a singlet. CH2, it will be split by this methyl, not by this OH, because the H is undergoing fast exchange. So this methylene will be split by the methyl only to give you a quartet. So this will be a quartet. And this methyl, by split by only the CH2, it will be a triplet. This will be the type of the spectrum for ethanol. Say for example, I am depicting the NMR spectrum of 2-propanol, isopropyl alcohol. I have added a small quantity of H plus, so that this proton in the functional group will undergo fast exchange. Result, it will not undergo splitting, it will not split the neighboring protons also. Therefore, I get two signals, one for this is for the CH, and the other for the 2CH3. In the ratio 1:6, 1:6, because for one, this is only one, you have 6 protons on the neighboring carbon atoms. And the signal of the OH will be very downfield. This is the signal of the OH. It will not undergo any splitting because I said it is undergoing fast exchange. So this will be the pattern. Let me tell you about the splitting pattern. This will not undergo splitting, it will be as it is. Here, there are 6 protons on the adjacent carbon atoms. They are equivalent. So this will be split into a septet. This will be split into a septet. Using the Pascal's triangle, you can find out what will be, that is, this is for 1 proton. If 2 protons are there, it is 1:1. If 3 protons are there, it will be 1:2, 2:1. For 4 protons, so you can construct the diagram and it will be a septet. According to this Pascal's triangle, you can show this as a septet. To be a septet. Now, let me spectrum of HD, deuterated hydrogen. Both have spin. H have a spin of half, and deuterium, which contains one proton and one neutron, has a spin value of 1. H having spin of half and D having a spin of 1. You can record the proton NMR of this, or you can record the deuterium NMR for this. How will the proton NMR look like, and how will the deuterium NMR look like? For proton NMR, for the hydrogen I get only one line. It will be split by the deuterium. What will be the splitting? I told you the formula. 2Ni plus 1 is the splitting pattern. 2 into only one deuterium is there, and the spin of deuterium is 1 plus 1. So that will be equal to 3. So this will be split into a triplet. The proton NMR will contain only one triplet, a single line which is split by the deuterium into a triplet. Suppose I am recording the deuterium NMR of this. For deuterium you will get a line. It is attached to a hydrogen, only one hydrogen. I use the formula 2Ni plus 1. Only one hydrogen is there. Spin of this hydrogen is half. I of this hydrogen is half plus 1. So this will be a doublet. This will be a doublet. Now, just for reference, I'll give you the precessional frequencies of various nuclei. We know that the precessional frequency depends upon the magnetic field applied. Say I have applied a 1.4 Tesla is the magnetic field. It is 14,000 Gauss I have applied. What will be the precessional frequency of various nuclei? The precessional frequency is also known as the Raman frequency. And the radio frequency needed is equal to the Raman frequency to cause the spin flipping, spin change. Okay, I am giving the precessional frequencies at a field of 1.4 Tesla. Proton will be 60. C13 has a spin of half. Abundance is very less, but it has got a spin of half. So the precessional frequency of C13 is only 15. Or for deuterium, one proton and one neutron, the precessional frequency is 9.2. N14 is also NMR active. It has got a spin of 1, and the precessional frequency of N14 is just 4.3. And for fluorine 19, that has got a spin of half. For fluorine 19, the value is 56.5. Very close to the frequency of proton. And P31, which is having a spin of half, it is 15.4. 15.4. I have given this. I have already told you if the Raman frequency is equal to the radio frequency, only then absorption will take place. That means C15, C13 will have only 15 megahertz as a precision frequency. So 15 megahertz radio frequency can cause this transition, so on and so forth. Now, when a signal splits into two, the spacing between the adjacent lines is called coupling constant. The spacing between the adjacent line is called a coupling constant. It is a measure of the magnitude of the splitting. The splitting is large, J will be large. How to calculate this coupling constant? It's very simple. This is a splitting pattern. If it is a doublet, the spacing between the adjacent line is the coupling constant. But the thing is, you have to mention or you have to express it in terms of hertz or CPS. Actually, we have been recording the spectrum according to the field strength only. It is a field sweep technique, I told you. So at this particular field it has split. I want this in terms of hertz, radio frequency. So how to calculate that or convert this into hertz? For this we follow a procedure. Namely, convert this into hertz or cycles per second. Before that, I want to tell you the J value is independent of the applied field. The signal is not like that. That is, the spacing between two lines very much depends upon the applied field. If the applied field is large, that spacing between two lines will also be large. So it depends upon the field, whereas the coupling constant J is independent of the field. That is one important information which you have to remember. And the size of the coupling constant, how large is the J value, depends upon number of the intervening bonds. Say for example, I have a proton here and a proton here. Number of intervening bonds are 1, 2, only 3 intervening bonds. So coupling will be more. There are some long range coupling also in a few cases. Namely, the intervening bonds between the protons will be more than 3. So J value depends upon all these factors. It doesn't depend upon the field. It depends upon the number of the intervening bonds. And of course, the spatial relation between the protons. By spatial relation, what I mean is, say I have two protons like this and two protons like this. We call these as geminal and we call this as vicinal. So I said the J value depends upon how many bonds intervene between the two protons and the spatial, namely whether it is geminal or vicinal. So I have a molecule where free rotation is there. Then of course anti and gauche forms are there. They will differ in the J value. Now, the magnitude of the J values. For geminal, J value will vary from 0 to 20. I said in terms of hertz. For vicinal, J value, this is for geminal. For vicinal, the value will be from 2 to 18. This is for the value. When you have freely rotating groups, the anti-conformation will have a J value of 5 to 12 hertz. And it is gauche. It will vary from 2 to 14. What I want to say is, depending upon the spatial arrangement, J will differ. It is independent of the field. It depends only on two factors I said. One is the number of intervening bonds and the other is the spatial arrangement, whether it is geminal, vicinal, anti, gauche, etc. Okay, now, how to convert the ppm value into hertz? Let us say I have recorded a spectrum with 270 megahertz. Now I get two signals. One signal, one peak at 4.21 ppm is one signal. And the other signal is 4.224. I get two signals, one at 4.21 and the other at 4.224. So the difference between them, I am talking about J value, it has split J value. In terms of ppm, I will say it is 0.014. I said it has to be mentioned only in terms of hertz. So how to convert this? The field distance is 270 megahertz I said. One peak I said is at 2.1, sorry, 1 minute. .21 is one signal and 4.224 is the other signal. Multiply them by the magnetic field distance. It is 270. The result will be, this is equal to 1136.7 and this is equal to 1140.48. Now take the difference. From the high value, subtract the low value. So it is 3.78 hertz. So J value is 3.78 hertz. The procedure is very simple. Find out the field strength at which the resonance occurs. I have two peaks, one at 4.21, other at 4.224. Multiply both of them by the applied magnetic field. I said we have recorded the spectrum at 270 megahertz. So now take the difference, subtract the lower value from the higher value, and what you get is J. This is how the coupling constant is calculated. Then I'll give some basic information regarding C13 spectra. Carbon 12 contains even number of neutrons and protons. It has no spin. I is equal to 0. So it is NMR inactive. However, in carbon, to a small extent, C13 is present. C13 has an I value of half, similar to proton. So C13 will be NMR active. So you can find out how many types of carbon are there, and in each type how many numbers are there. That you can find out. And the chemical shift range, in the case of proton NMR, it ranges from 0 to 14 ppm. Since abundance is very, very low, the abundance is only 1.1%. So if you will be having 98.9% C12 and only 1.1% C13. And the chemical shift value varies from 0 to 240 ppm, a very large value. Okay. Say for example, I am recording the C13 NMR of ethanol. This will absorb at a low field and this will absorb at a high field because this is attached to an electronegative atom. So I get two peaks for carbon 13. Methylene peak at a lower carbon at a lower field and methyl at a higher field. And delta value, this will be at 20 ppm and this will be at 60 ppm. Since the abundance is very, very low, no splitting between the carbon atoms could be seen. No splitting between the two carbon atoms could be seen since the abundance is low. So the spectrum will contain simply two lines, one at 20 ppm and the other at the 60 ppm. This is the shielded carbon and this is the de-shielded carbon. We said that between the adjacent carbon atoms, splitting pattern will not be there. Since the abundance is very, very less, you get single peak for each carbon. However, the hydrogens attached to the carbon, they have spin, they will split the carbon signal. Then the spectrum will be complicated. To avoid this, we decoupled the proton. What is meant by decoupling? Using a secondary radio frequency, if we excite that particular nucleus which has to be decoupled, that will undergo fast transition. Whenever a nucleus undergoes fast transition, it cannot split the signal of the other. So whenever we record the C13 NMR, we give radio frequency corresponding to protons in a perpendicular direction so that all the protons get excited and they can't split the carbon. So C13 spectrum is always a proton decoupled spectrum. Well, here I have given the chemical shift values of some of the carbons. Ketones will have a chemical shift of 205 to 220, aldehydes 190 to 200, acids and esters 160 to 185, aromatic carbon 125 to 150, alkenes 115 to 110, RCH2O 50 to 90 and RCH2NH2 30 to 65. The list is endless. Different carbons we have give. So this is how C13 spectrum is recorded, and you get information about how many different types of carbons are there in that.